Our next focus here is thinking about star spectra and what kind of information we can get from a star based on looking at these spectral lines that they're projecting. So the best way to think about these spectral lines is like a fingerprint. We know a little bit about human fingerprints, so go ahead, kick it off right away. On the right side here, why are we saying that fingerprints are used to identify a criminal? Why are they a reliable way? So pause the video if you need to, take a quick sec, fill in that right-hand side. Well, we know fingerprints for every single person are individual, right? They're unique. No two people have the same fingerprint. So you can use your fingerprint to scan into your phone. No one else can do that because every single one is different and they never change, right? So it's a great way to identify a person, okay? Elements do the same thing, or stars. We talk about a star spectra as like a wavelength of light given off by a star. Now the stars containing different elements, therefore, they emit different patterns or different wavelengths of this visible light. And we started looking at these in class during our fingerprinting lab. This one is pretty in-depth, right? Lots of different wavelengths here, but we can see that pattern is our visible light that we looked at on our wavelength chart a couple units ago. We saw our 700 is in that red. As that wavelength shortens, it changes color all the way down here to that bluish purple, the shortest wavelength. So that means that this object, this light source that we're looking at, is emitting energy at all these different wavelengths. There are a couple black areas there. Those are spaces where no energy is coming. So it's like a key, a fingerprint to this light object. Now, elements have their specific fingerprints, right? They emit a unique set. Every one, like we said, is different. So here's that very intense spectra that we looked at, and then here's a bunch of different elements. So if we're looking and comparing, what we can do is try to identify, well, what elements exactly am I seeing here in the observed spectrum? So I would look, okay, my hydrogen, right? Does that match up? And if I see all the hydrogen fingerprint lines in the observed spectra, then I know it would be present in that star, right? As I start to trace some of these up, like helium, right? I'm seeing those match up. This one is a match, okay? So as I continue to see those different parts showing up in that spectra, I then know those elements are part of that star. So composition is really the number one thing that we're going to use our spectral lines for. We're going to use it to figure out what these elements are made of, right? It's like the ingredients of a star. And again, we're comparing those spectral lines of elements to the star to figure out if it's a match. We can also use it to figure out the energy level of the star, right? Depending on the color. If it's more red, we know it's a longer wave, weaker type of energy, more blue, more powerful. Same with temperature, right? Directly connected to energy, how hot or cool the star is. Remember, kind of tricky to say the star is cool. It's not cool, it's just cooler. Other things that we can look at over time, we can compare its motion over time, kind of what we're seeing here in this animation. As this object is moving around, we can notice its spectra shifts, therefore telling us if that star is moving towards or away, red shift, blue shift, if the star might be rotating, and if it has a certain speed to it, how fast it's moving. So all those things are clued in just by comparing these spectral lines. We talked a lot about red shift, blue shift last unit. So just wanted to show you an example. Here's the regular or traditional spectrum, right? So now when I look at these spectral lines in the red shift, I can see instead of being in their correct location, they're shifted a little bit this direction, right, towards the red end. Whereas the bottom, the blue shift, again, this is its location where that wavelength should be, but I'm seeing it here shifted a little bit towards the blue end. That would clue me in that this object is moving towards us. So got an example of that for you to try on the right-hand side. Take a look at the original spectra. I marked a couple lines for you so you can compare the location of 1 and 1 in both spots, 2 and 2, 3 and 3, and decide, are you looking at a red shift or a blue shift? And most importantly, how do you know, right? What are your clues that you're seeing? Now, the most common thing we're going to use the spectra for is composition, right? What the star is made of, what elements make up that star. So by simply lining up those spectral lines, again, we're trying to look for a match, right? We're looking for a 100% match of the element in the star. So here's our star down here at the bottom. We want to know, are these calcium lines present in the star? If we see those, we know there is a match. If we don't see them all three present in the mystery star, we know calcium then would not be part of it. So my best bet is in notability, if you use that line tool, you can make that straight line and come down and see, is that element line part of the star? So just circle up which ones you think are present. And a little explanation of how you did that. So at this point, you're done with that notes section. Just a reminder, you want to be going over to your study guide, and all the notes we just completed are going to help you out with Learning Target 3. As you work Learning Target 3, you should be using these terms somewhere in your written summary. And every time you use one of those terms, make sure that you highlight it up so I can see that you've explained this idea using those 4 key words. As always, reach out for any questions you have.